Swayam Prabha. Digital India. Educated India.
So, welcome to the 39th lecture of Cryogenic Engineering under the NPTEL program. So, we have covered several topics till now, and just to get a glance of what topics we have covered under Cryogenic Engineering is introduction to Cryogenic Engineering, properties of cryogenic fluids, properties of materials at cryogenic temperature, gas liquefaction and refrigeration systems, then gas separation, cryocoolers, cryogenic insulations and vacuum technology. Going ahead from here, the current topic is focusing on instrumentation in cryogenics, specific instrumentation related to temperature, for example, or pressure and flow rates, etc. We can do a lot of instrumentation required in cryogenics. Under this topic, we will understand what is there as a special need for cryogenic instrumentation, what is that is more demanded in cryogenic instrumentation, and then measurement of thermophysical properties. We will study a few properties and how do we measure these properties at low temperature. Then we can see a few sensors for measuring this thermophysical property as to how these sensors work, what are these sensors and things like that. And we will cover this topic in around 3 lectures. We will just touch upon various properties and the sensors and how do they work, etc. And finally, we can have different tutorials and assignment as we have been having under different topics till now. So, topic is therefore instrumentation in cryogenics. Let us understand the need of cryogenic instrumentation. What is the special need in cryogenic instrumentation as compared to what we do at, for example, room temperature? Measurement of thermophysical properties. And what are these properties? Temperature, that is what we will cover in this particular lecture. Introduction. In the earlier lecture, we have seen that the cryogenic vessels are insulated and they are closed containers. So, this is a cryogenic vessel and you got some cryogen in that and you got some insulation or vacuum around it. And in order to monitor particular experiment going on this closed container, we require to have instrumentation and it is needed to monitor the vacuum in insulation as there is a continuous gas in leak. So, for example, there is a vacuum between this inner vessel and the outer vessel and we need to monitor this vacuum because based on this vacuum or insulation, the boil off of this cryogen will be dependent. So, let us say we have got a vacuum over here, we need to monitor this vacuum and therefore, the pressure needs to be monitored or there should be some indicator so as to know if this vacuum is coming down. As the vacuum will start coming down, the radiation losses convection losses will increase in this system and the boil off will be more and more. So, basically we need to have some gauge in order to monitor. If I want to do some instrumentation on this experimental cryostat in my laboratory, I will have to worry about the vacuum that is produced between the inner and the outer vessel here. Also, I would like to monitor the liquid level so as to avoid any overflow of the cryogen. Or if I have to monitor that, if I got a sample of which I want to measure the temperature or I want to do some experiments to monitor the properties or to understand the properties at low temperature, for example, conductivity of this material, etc. at low temperature, this level of the cryogen, let us say liquid nitrogen, has to be monitored at a particular place. As soon as this level starts going down, I will have to add in some liquid nitrogen or a cryogen, or I should not add cryogen to a level because of which it will start coming out. So, it is very important that I monitor the liquid level of this cryogen that is put in this particular cryo container, and therefore, we will have to have some gauge which will monitor this liquid level, all right. And also, we have to monitor the sample's temperature. For example, I got a sample which is kept at this point and I have to measure some property of this sample, let us say conductivity or specific capacity or shrinkage, for example, whatever at low temperature. and therefore, I need to have this sample at different temperatures. All right. So, I need to have some sensor which is sitting on this sample, so that I will know at what temperature the properties are being measured. So, there are various ways, and therefore, there are various properties that could be monitored in a cryogenic experiment, but this is a very small experiment that could be done in a laboratory scale, wherein I would need to monitor the liquid level, I will need to monitor the temperature of this sample with time, and accordingly I would also monitor the pressure or the vacuum that is being generated by a vacuum pump over here. This will ensure that the boil off does not increase. This will ensure that whatever the properties I want to measure, they are measured at a particular temperature, and also the liquid level gauge will ensure that the pre-required amount of liquid that is always getting maintained in this cryostat. So, instrumentation is needed like this for various applications. Some applications may not require, for example, vacuum to be maintained, but some applications will require some other measurements to be done, all right, and therefore, it is very important. Some application may require to see at what rate the boil off is happening. The mass flow which is living in this particular place needs to be monitored. So, there are various things that needs to be monitored, and therefore, special instrumentation is required to be done at cryogenic temperatures. So, this justifies the need of instrumentation for a safe cryogenic operation. It is clear that conventional methods like Borden pressure gauge or thermometer cannot be used due to following reasons. So, I can't have a Borden pressure gauge which is maintained to measure the vacuum over here, because I got a negative pressure here, I got a vacuum being generated at this point. Also, I can't use thermometer with mercury at this point here. All right. So, I need to worry about some other instrumentation mechanisms, some other sensors which will work at very low temperatures, and it will also satisfy other requirements at which are going to be very special at lower and lower temperatures. What are they? These sensors have to work at extremely low temperature. All right. For example, I got a mass flow measurement. The mass flow is going to be measured at low temperature. The boil off is going to be at lower and lower temperature. So, these sensors have to stand those low temperatures. All right. The liquid level sensor, which is going to be kept inside the liquid, has to stand that low temperature. It's very important, because at low levels, at low temperatures, the material will undergo a lot of changes, and therefore, sensors has to be correctly made in order to stand those low temperatures. Also, the sensor has to sustain, it should have the sustainability to thermal and mechanical fatigues. So, after some times when the cryogen goes off, it will come to room temperature. Again, when you put the cryogen, the temperature will go down, and therefore, the sensor has to stand this thermal and mechanical fatigue. As the temperature goes down, it will shrink, for example, or as the temperature comes to room temperature, it will expand again because of change of temperature. So, this will happen many times, and therefore, the sensor has to stand or sustain this thermal and mechanical fatigue. Third important thing, all these calibrations have to be done at low temperature. All right. So, whenever I develop a sensor, if I want to measure the sensor temperature, I want to measure the temperature up to 1 Kelvin, then I have to have a known 1 Kelvin source. The calibration has to be done with respect to this known standard 1 Kelvin, 1.2 Kelvin, 4.2 Kelvin, whatever. These sources have to be standardized. So, calibration at low temperature is not going to be very easy. So, liquid level sensor, if I use it for water, it will work in a different way, but if it is going to be sensing the liquid level at 77 Kelvin or 4.2 Kelvin, then I cannot use the sensor which is being used for water, for example, because the sensor at 4.2 Kelvin will undergo completely different transformation. It will be working at low temperatures, the sensor will get shrunk, and again it requires to be calibrated at this temperature. So, the sensor which are going to be working at low temperature has to satisfy all these conditions, and therefore, the sensors normally which are working in cryogenic conditions are very costly. This one has to keep in mind, and therefore, they are not only very costly, if you want it calibrated, for example, if you want to calibrate it to a very higher accuracy, again you are charged for that thing. So, accuracy requirement at low temperature also is a question mark, because the cost of the sensor will be accordingly decided. All right. So, this requires a very special setup meant for cryogenic condition. So, what are the special requirements for the sensors to be working at low temperature? There are a few special requirements that are to be qualified by the sensors to use them in cryogenic technology. They are remote arrangement. That means, the cryogenic vessels are closed containers. The sensor should be capable of remote operation from outside, because the sensor is going to be kept at low temperature while the leads will come out, the wires will come out, and at room temperature you will have a display unit. So, sensor actually working away from the actual measurement place, and therefore it is kind of a remote arrangement, and this remote arrangement should take care of all the wiring that should come out from inside to outside. It is a very important requirement. Vacuum. The sensor should be able to withstand the low pressure prevalent in vacuum. For example, some sensor may have to work with vacuum, especially the pressure measurement sensors, alright, or some sensors are working at low temperature and they are also working in vacuum. For example, a temperature sensor working in a cryocooler. The cryocooler will have vacuum all around it, and the sensor also sees vacuum, and therefore the sensor leads have to come from vacuum and it have to come outside. So, this also has to be taken care of while working in cryogenic or while working in vacuum atmosphere. This is a very important requirement. You have to have a very special kind of seals which seals vacuum from the atmosphere. So, you got to have some special seals for this purpose. Cryogen, the sensor should be chemically inert towards the cryogen under use. So, the sensor should not, the material in sensor, whatever is being used, should not react with, for example, liquid nitrogen, or there are other inert cryogens basically, but some gas, for example, liquid hydrocarbon should not interact with this sensor. Otherwise, we will have different chemical reaction, and therefore, the characteristic of the sensor will completely change. Sometimes the sensors have to work in magnetic field, and therefore, the property of the sensor should be intact even in the magnetic field atmosphere. You have to see that the magnetic field, for example, in MRI, there will be a lot of magnetic field, there is a good magnetic field, and the sensor properties should not change under the magnetic field. For example, silicon diodes cannot be used therefore under the environment of magnetic field, but I have to use Cernox for temperature measurement. Very important deviation when I have to think about when I go for a magnetic field environment. Accuracy, of course, is very important. The accuracy of the calibrations are very important at such low temperatures, and one has to pay for this. The losses, the heat release, for example, I square R, because there are leads coming from the closed containers to outside, and therefore some current will go inside, and therefore some heat will be getting released because of the I square R losses, or conduction via leads, because one end of the sensor is going to be at room temperature, the other end of the sensor is going to be at low temperature, and therefore some conduction may occur, and that also can cause some errors in your measurement. So, the losses because of the conduction across the leads and I square R losses, you have to see that these losses are taken into account while calibration. These errors have to be taken into account basically. And the material properties, the thermal mechanical property of the sensor must be in the allowable limits. They should not be subjected to extra stresses. They should not be subjected to a lot of thermal stress also. And therefore, this property also have to be taken into account when you design a sensor for cryogenic conditions. In fact, the cryogenic sensors therefore will have to stand against all these odds which are normally not existent in room temperature or otherwise used in normal experiments. Alright. So, there are various thermophysical properties, and these sensors have to stand all those requirements which we just defined. Now, let us see what are these thermophysical properties which are required to be measured. There are various thermophysical properties that are measured or monitored in cryogenics. They are temperature, liquid level, pressure, mass flow rate, viscosity and density, electric and thermal conductivity. In addition to that, we can have specific heat capacity and things like that. Some property like magnetic susceptibility and things like that, but out of which we are going to study mostly that are used in cryogenics will be temperature, liquid level and pressures. This course will look at these three property measurements, and in this particular lecture, let us focus on temperature measurement. In this topic, only the first three properties are covered, which are very, very important, and normally that will be used mostly in the cryogenic operations. So, let us look at temperature. Various measuring units of temperatures are Kelvin, degree centigrade, degree Fahrenheit, Rankine, etc. The measurement of temperature is based on zeroth law of thermodynamics. It states that when two bodies are in thermal equilibrium, they are at the same temperature. Alright. That means I need to have some calibrated data in which the sensor to be calibrated will come in contact, and then you can say that they are in thermal equilibrium, and then we say that they are at the same temperature. Alright. So, it is very important that we keep two units in a good thermal equilibrium with each other and see to it that they are in perfect thermal equilibrium, and therefore, in this way we can calibrate a sensor at very low temperature. Temperature is measured to monitor thermal expansion and most importantly pressure. So, why do we require? Of course, we have to know the temperature by itself, but it can also have an indirect, based on the temperature you can monitor thermal expansion. At the same time, we can see what is the pressure rise of a cryogen with an increase in temperature. All right. So, temperature is an indicator of a lot of things actually in cryogenics. The calibration of a temperature sensor is done using some fixed point. This is a very important thing, as I said. At room temperature above, we have got various fixed points, but if you want to do calibration of a sensor at very low temperature, we have to go by some fixed point or conventionally fixed point, which are very known temperatures, and this data is very important. We have to have the data regarding these fixed points. What are these fixed points? This fixed point use temperature scales, and the international temperature scales is defined up to a triple point of hydrogen. For example, its value is 13.84 Kelvin. So, I know at a particular pressure above hydrogen, I will get a triple point when the hydrogen will get solidified, and that temperature is 13.84. This is a very defined temperature. I know liquid nitrogen temperature, all right. I know the 0 degree centigrade ice temperature. I know the boiling point of water. They are all fixed points. But in lower temperature range, we have got, for example, the triple point of hydrogen as a fixed point, which is universally accepted. So, if I want to do measurement, I can take this as a very important point, and against this I can calibrate my sensor. Recently, various scales are developed to measure much lower temperature. So, if I want to go to 1 Kelvin, below 1 Kelvin or below 10 Kelvin, there are various fixed points which are again universally accepted. For example, germanium resistance thermometer, which normally give calibration from 4.2 Kelvin to 13.84 Kelvin. So, below hydrogen triple point, we have got now germanium resistance thermometer that also could be used as a function of resistance versus temperature. So, as soon as the temperature changes, the resistance changes, and we know the relationship between this temperature and the resistance, and therefore, we can calibrate a sensors below 13.84 Kelvin up to 4.2 Kelvin using germanium resistance thermometer. Then below that we have got a helium vapor pressure, helium 4, which is an isotope, as you remember. So, we can characterize our sensor or calibrate our sensor from boiling point of helium till 1.5 Kelvin, which is going to be at lower and lower pressures now, below atmospheric pressures. And it was invented in 1958, and this is normally called as T58 scale or helium 4 scale, which is developed in 1958. So, below 4.24 Kelvin up to 1.5 Kelvin, I can use helium 4 vapor pressure. That means, how the vapor pressure of the helium varies below 4.24 Kelvin. So, there is again a calibration curve with respect to vapor pressure curve versus temperature, and that also can be used to calibrate sensors below 4.24 Kelvin. Then we have got a helium 3, which is again an isotope of helium gas, and we have got a vapor pressure of helium as a scale up to 0.8 Kelvin. So, below 1.5 Kelvin up to 0.8 Kelvin, we can use a helium 3 vapor pressure curve to calibrate, and this scale is all called as T62 Kelvin because it was invented in 1962. For the temperatures between 0.006 Kelvin up to 0.8 Kelvin, the scale is based on the properties of cerium magnesium nitrate, the salt. So, you got a various properties of this salt that could be now brought in, and the temperatures in this range can be calibrated. And then below that, the variation in magnetic susceptibility of this salt are calibrated in terms of temperature. In this temperature, what is basically calibrated is magnetic susceptibility of this salt. Alright, so these are different temperature scales that are used to calibrate different temperature sensors. The temperature measurements, various sensors that are often used in cryogenics to measure temperature are thermocouples, metallic resistance thermometer, semiconductor resistance thermometers, constant volume gas thermometer, vapor pressure thermometer. Most of this, thermocouple is mostly used at various applications for high temperature as well as for low temperature. At low temperature, again you got magnetic thermometer, which is what we just talked about. So, mostly thermocouples, metallic resistance thermometers and semiconductor resistance thermometers will be used for normal applications in cryogenics. Alright, so I am going to focus on these three parts, and mostly we will talk about thermocouples in the present lecture. Alright, so let us come to thermocouples now. So, how does it work? Consider two conducting wires of different materials. For a thermocouple now, we have got a material A and material B. So, you can see a wire of material A and wire of material B, and you got a joint here, let us say left joint and right joint. All right. These metal wires are joined together as shown above. The left and right joints respectively are LJ and RJ, and that means if you connect metal A with metal B, wire A and wire B at left joint, and you got other connections, we got two different connections and we got a voltmeter across between A and B now. So, what happens? Consider a situation in which left and right joints are maintained at T1 and T2 respectively in such a way that T1 is not equal to T2. So, I got a left joint at T1 for example, and I have right joint I have kept at T2 for example, such that T1 is not equal to T2. If such a thing happens, then due to the temperature difference, a net voltage or an electromotive force EMF is developed in the loop, and this is called as Seebeck effect. This most of you know. All right. So, because of these dissimilar metals joined together and because of the temperature difference between T1 and T2, a voltage gets generated, an EMF gets generated, and this EMF is nothing but function of these two temperature difference T1 minus T2. All right. Now, this is called as Seebeck effect. It is named after a German physicist Thomas John Seebeck in 1821, which is the old technology actually. The voltage E is normally in millivolts, is directly proportional to the temperature difference. So, it is going to be proportional to T1 minus T2, which is denoted by a small t in degree centigrade. Mathematically, therefore, we can say that this E or the EMF which is generated is going to be function of this temperature difference. So, actually what you develop therefore is the calibration curve. You can have a voltage that is generated in millivolts as a function of this delta T, all right. Or we can also call this as temperature difference as a function of E. I can relate now temperature difference as a function of whatever EMF gets generated because of the temperature difference T1 minus T2, all right. Here F and G are some functional correlations. I can always develop some curve if I know various T values, and corresponding to that T values I know various E values. So, I can find out a relation between T and E. In practice, so what do? I want to use this Seebeck effect now to measure temperatures. So, what do? I keep a reference point like ambient temperature or ice point is maintained at the left hand. So, I keep T1 as a very standard value which I know, ambient temperature for example 300 Kelvin or 0 degree centigrade if I put ice at this point. If I keep T1 as constant, and if I want to measure now T2 value of a particular cryo cooler for example, I will dip or I will touch that material. For example, I can dip this in liquid nitrogen also, which is 77 Kelvin. So, depending on the difference between T1 and T2, I will get some EMF generated at this point, and this EMF is going to be directly dependent on T1 minus T2, and I will have this correlation in my hand, which is basically coming out of some calibration technique, and therefore, I will be able to relate this EMF generated to T1 and T2, of which I know T1. Because T1 is kept constant, and therefore, I can calculate the value of T2 easily, and this is the way a thermocouple works. The temperature at the right end is calculated using functional correlation. These functional correlations are also dependent on wire material, wire dimensions and the reference point. So, depending on what I am using over here, what is the thickness of this wire, what is the length of these wires, material of this wire, I will find out the relationship between that. Some approximate values for different types of thermocouples are given below. There are various types of thermocouples depending on the material that are used as different joints. There are T-type thermocouple, K-type thermocouple, E-type thermocouples. So, when I talk about T-type thermocouples, they are basically copper and copper nickel alloy, that is copper constantan. So, one joint is copper, other material is copper nickel alloy, which is constantan. This is normally called as T-type. It has got a range of calibration between 3K to 673 Kelvin. So, quite a good range which covers from cryogenic to high temperature range, and sensitivity of around 4.6 microvolt per Kelvin at 20 Kelvin. All right. This will increase at higher and higher temperature, but at low temperature it still has some sensitivity. All right. So, you got a 4.6 microvolt variation per Kelvin at around 20 Kelvin. Then we got a K-type thermocouple. It is made up of nickel and chrome, which is called as chromel, and nickel and aluminum, which is alumel. All right. So, we got a chromel aluminum or a K-type thermocouple. The two materials are chromel and alumel. All right. Here the range is again from 3K to very high temperature 1543 Kelvin, K-type, and sensitivity is around similar to what we have for T-type. 4.1 microvolt per Kelvin change at around 20 Kelvin. Alright, so sensitivity also is not very small, it is a reasonably good sensitivity. So, we have seen T type and K type thermocouple, and then we got a E type also, which is also made of, it is called as chromel constantan now. So, we got a nickel chromium as one material A, let us say, and copper nickel, which is constantan, as a material B basically. So, this is called as E type, where we have got a chromel constantan thermocouple. It is again used for a range of 3K to 953 Kelvin, and the sensitivity is around 62 microvolt per Kelvin at 20 Kelvin. So, you got a high sensitivity as compared to T and K type over here. So, E type thermocouples are really acceptable. I would just like to show you here a thermocouple which is over here. Can you see this thermocouple? So, this is a joint which you can see at this other end, while this is a one joint, I can say left joint, and the right joint can be, I can connect a voltmeter between these two, and this voltmeter itself gets joined by, at a room temperature joint basically. So, you can have a material A as this red one, and you got a material B as this yellow wire. One joint will be at ambient temperature, and I can have a voltmeter connected right over here, and the other joint could be the temperature. If I want to measure whatever temperature I want to measure, this temperature would come over here. So, this is a simple thermocouple that you can see. You got a one joint here, you got a other joint here, and other joint will have a ambient temperature. We can have a voltmeter placed across these two lead wires. Alright, so let us go back to, so we have seen now T type, K type and E type thermocouples. They got different sensitivity, they got a different range of temperatures to be measured. This combination produces the highest Seebeck effect, as we can see for E type thermocouples. Now, you can see the sensitivity or a Seebeck coefficient over here as compared to temperature. The adjacent figure shows the variation of Seebeck coefficients with temperatures for E, K and T type thermocouples. So, you can see a E type thermocouple, and you get a Seebeck coefficient over here, and the Seebeck coefficient is basically what is the voltage change that happens per Kelvin change over here. So, you can see E type, K type and T type, and at any temperature you can see that E type has a very high sensitivity, high Seebeck coefficients, which is microvolt per Kelvin. What is the microvolt changes that happen per Kelvin? So, adjacent figure shows the variation of Seebeck coefficient with temperature of E, K and T type thermocouples. For any given temperature, E type thermocouple has more Seebeck coefficient than T type thermocouple. That is what we see. It is important to note that the sensor should have a maximum coefficient for greater accuracy. Therefore, it is very important that this works. Mostly the E type will be preferred in that case. Hence, E type thermocouples has more accuracy than the T type thermocouple. From the figure, it is clear that the temperatures below 50 Kelvin, if I come below 50 Kelvin, the microvolt per Kelvin is going to be less and less, and therefore, normally thermocouples will be used, let us say above 50 Kelvin temperatures. Of course, one can come down over here, but the sensitivity will be less and less, and therefore, you will have to increase this microvolt, you have to amplify the output or the EMF to a greater level in this case. So, here normally we will have thermocouples measurement to be done normally up to 50 Kelvin. Alright. It is undesirable to use these sensors in this temperature range. So, below 50 Kelvin, I will not normally use thermocouples because the sensitivity will be now questionable, and therefore, the accuracy will be questionable. Now, what are the disadvantages with thermocouples? There are some disadvantages. The EMF or the voltage generated is very small, typically in the order of millivolts. A series combination of various thermocouple is therefore used. So, if I want to increase that millivolt to some volt, I will have to amplify it, and therefore, I will to use series of thermocouples to increase this millivolt to some measurable voltage level. So, one can have some errors in this. You need to have some amplifier circuit also. The voltage drop across the length of the lead wires induces substantially, there are some errors in measurement, as we say, because we got a long wire which is coming over here, and therefore, there could be some voltage drop across it that also will cause some errors in the thermocouple temperature measurement. The thermal conduction along the lead wires contribute to the heat in leak also. So, you got some, because at the lower temperature on the other side and higher temperature on the other side, there will be some temperature conduction, thermal conduction that will be happening, that also will cause some error of measurement, and one has to take this error into account while using thermocouple for temperature measurement. So, after the thermocouple, just now we have seen how the thermocouple works and how it is used in cryogenic conditions. We got the next sensor, which is resistance temperature detector, or normally called as RTD, which is most prevalently used to measure temperatures at very low temperatures, let us say up to 30 Kelvin temperature. It is very commonly used. It overcomes most of the disadvantages that a thermocouple normally will have, and therefore RTDs are very popular in cryogenic temperature measurements. Resistance of a conductor or a semiconductor changes with the change in temperature. So, basically this is the relationship between the resistance and the temperature, which will be known to us, so the calibration becomes simple. Resistance temperature detectors, also called as RTDs, use this property, that means the relationship between resistance and the temperature, to measure the temperature. So, one should calibrate the change in resistance that occurs with the lowering of temperature. If this standard calibration is known, if this relationship is known with us, we can formulate also an equation, and against the change in resistance we can find out what is the temperature that is correspondingly exist over there. Platinum, copper, lead or indium wires are used in the metallic RTDs. So, the resistances of these particular materials change with temperature, and this change of temperature is going to be related to the changes that occur in resistance of these particular materials. Non-metallic RTDs use GaAs, gallium, aluminum, arsenic diodes, carbon glass and ruthenium oxide. So, these are the non-metals that also could be used, whose resistances change with lowering of temperature. The resistance change also can get calibrated across with changes that happen with temperature. So, they also can be used to work at low temperatures. So, this is how a sensor would look. A typical sensor, RTD sensor, and normally I am talking over here platinum sensor, because this is what mostly will be used in cryogenic applications. This costs also little less, let us say around 1000 rupees per small sensor, which may not be calibrated or which you have to calibrate sometimes, and the calibration of this actually is simple. The schematic of a platinum RTD is as shown in this figure. A conducting wire, say platinum wire in this case, of very long length is wound on a notched mica insulator. So, you can see a mica insulator over here, alright, and this mica insulator has got notch made around, across which runs this platinum wire, alright, and this platinum wire is now, the entire thing is going to be actually covered under this platinum sheet, alright. This assembly is housed inside a closed platinum sheet. So, if I want to measure a particular temperature, this sensor will be exposed to that temperature. This entire thing is sensor, and corresponding to this temperature, its resistance will change, which will be measured from these leads. Very simple application. This sensor has to be in thermal contact with whatever temperature you want to measure. For example, liquid nitrogen, I can just dip this sensor in liquid nitrogen. Corresponding to this, I will get some ohms associated with this temperature. Normally around 21 to 23 ohms is what you will see at liquid nitrogen or 77 to 80 Kelvin temperatures. An ohm meter is used to measure the resistance, thereby the corresponding temperature. So, depending on the temperature to which this platinum Cs are exposed, I will get some ohms across these leads, which are kept at room temperature. So, I will have a long leads which may come out, and therefore, I will measure the resistances across this platinum wire, which sees a particular temperature to be measured. A simple operation. The photograph of a RTD as shown over here, and you can see the sheath, the platinum sensor and the long leads. Now, I have shown you a schematic, and I will show you the sensor also, which we have here with me. So, you can see I have got this sensor, and I will just take this sensor out. Normally, you should handle this sensor with care. You can see these two wires or the leads coming out of this, and inside this is a platinum wire which runs through the mica sheath, and there is a platinum sheath also. So, normally what you can see is some kind of square over here and having 2 or 3 leads coming out, and these leads, then you can connect wires to these leads, so that you can have a temperature measurement to be done at room temperature. Alright. So, you see here platinum wire at the other end, you can see the sheath also and the lead coming out of this. So, simple PT100, what you can see, a platinum sensor and RTD over here. Alright. So, let us come back to our slide. So, exactly it looks like what I am showing here in the slide. So, you got leads, two leads, you got a PT wire which is what you just saw, and you got a sheath also which is covering this platinum wire. So, that this should not get accidentally, you should not tinker with this PT wire, which will change the resistance, and accordingly you can have errors in measurement. So, the photograph RTD is as shown over here. The typical size of a RTD is 3 millimeter into 1.84 into 0.98. So, you can see that the lengthwise little longer, width and height is just a millimeter actually, a very small one. So, what is most important is that this particular sensor should be kept in thermal contact with the temperature you want to maintain. So, you can have a flattened surface, so that you can have a maximum area of contact, so that the two are in good thermal equilibrium, which is very important. Fixing a thermocouple for example, or also an RTD to the surface temperature of which you want to measure is very important. They should normally be having some kind of a grease, alright, we call it thermal grease, so that the resistance is minimized between these two measurements. They are in good thermal equilibrium with each other, alright. So, these are very important things of actual experimental cryogenic techniques. So, here we have got a curve between the resistance variation with temperature, and this resistance measurement is actually RT by RO, that means the resistance at any temperature T divided by resistance at 0 degree centigrade. So, the choice of the wire material is dependent on the variation of resistance with temperature. The adjacent figure shows a variation of RT by RO or R0 with the temperature. Okay. So, you can see that the temperature variation or non-dimensionalized resistance RT by RO with temperature, as you lower the temperature, the RT value starts coming down. RO is a constant temperature, constant resistance. Here RT and RO are the resistances at temperature T degree centigrade and 0 degree centigrade respectively. So, R0 or RO is a constant, while RT is going to vary. If I lower the temperature, the resistance RT will start coming down, alright. And you can see this is as good a linear variation up to a particular temperature, and this becomes non-linear at a temperature let us say below 50 Kelvin. So, having a linear relationship is always better, and I can actually fix a y is equal to mx plus c kind of a curve, which is a linear variation from let us say 50 Kelvin up to 300 Kelvin. That is my cryogenic temperature region. So, it is very good for calibration. If I measure the temperature, for example, if I want to calibrate, I can put it liquid nitrogen and I can get it resistance, and I can get a resistance at 300 Kelvin. If I get these two value, I can just join them by a central line, by a line, and I can extend this line further up to 50 Kelvin, and I can have an equation of calibration curve for a given RTD. This is a very important and therefore simple calibrations. Just dip it in liquid nitrogen, get the value at 77 Kelvin, get the value of the resistance at 300 Kelvin, have these 2 points and extend the line further, and I can depend on this curve up to 50 Kelvin with a good accuracy of around 1 Kelvin. This is a normal process of calibration of a RTD or a PT100. If you want to do further, if you want to go very, very close and want to increase accuracy, then I will have to go for small intermediate points also, alright. It is desirable to choose a material whose resistance varies linearly with temperature, and that is why PT platinum is preferred, because there is a linear variation of resistance with temperature. But you can have otherwise variation, but then I have to worry about all the intermediate point at different temperatures. From the adjacent figure, it is clear that the sensor is most preferred up to 30 Kelvin. So, one can go up to 30 Kelvin, in fact up to 50 Kelvin or 40 Kelvin, as I said, the curve is linear and you have to have some other values below and up to 30 Kelvin. Below 30 Kelvin, I will not use PT100 unless I got a fairly good accurate calibration done up to 20 Kelvin-ish. Okay. So, 30 Kelvin, as I say, this that the variation is acceptable. The correlations for the adjacent graph is RT by R0 is equal to 1 plus AT plus BT square plus CT cube plus into T minus 100. I mean, you can have this curve fit up to 30 Kelvin. I would have only 1 plus AT curve up to let us say 50 Kelvin-ish, because there is a clear linear variation that is happening up to 50. But if I want to have a calibration up to 25 Kelvin or 20 Kelvin or 30 Kelvin, I will have to go for a BT square and CT cube and this kind of. This is the temperature which I see at a particular temperature. Alright. So, I can fix up a curve and this can be fed to the whatever software you are using. So, the moment you measure this value of T or resistance, I can get the value of temperature done. I can get the value of temperature immediately. The constant A, B, C are found by calibration of RTD at any 3 standard temperatures. So, I can have 100, I can have 300 Kelvin, I can have 273 Kelvin, it is 0 degree centigrade, I can have 77 Kelvin. These are my 3 points based on which I can get A, B, C. But I need to have one more point below over here, which is below, I should have some source which will definitely give me 20 Kelvin, 25 Kelvin, so that my curve is fairly accurate. This can be given by a cryocooler also. Now, if I want to see the sensitivity of this, so this is sensitivity curve with temperature. The term sensitivity is defined as the rate of change of electrical resistance with the change in temperature. Mathematically, it is expressed as S is equal to dR by dt. So, how my resistance change happens with the change in temperature. So, you can see that resistance change is fairly high up to let us say 50 Kelvin temperature, and then it comes down. So, that is why the sensitivity is very high, let us say up to 30 Kelvin, and below which the sensitivity decreases. The adjacent figure shows the sensitivity platinum resistance thermometer. The advantages of a RTD are this sensor exhibit a very high repeatability and accuracy in their operating range. Few typical values for this sensor are the repeatability is plus minus 10 millikelvin in 77 Kelvin to 305 Kelvin, which is fairly acceptable in our normal measurements of temperature. Unless if you want to go deep down, I mean less than millikelvin region, then you will have to have a very good calibration done, or you will have to go for other sensors like silicon darts, etc. But then for which you will have to pay a very high amount. The accuracy is plus minus 250 millikelvin again in this temperature range, which is also acceptable to me. In fact, for me is plus minus 0.2, 0.3 or 0.5 Kelvin is acceptable actually. The effect of magnetic field is very low for the operating temperature above 40 Kelvin. So, this is acceptable even if this sensor was in magnetic field environment. There are not much errors that is going to be, the calibration still holds good basically, and therefore, this is a very important thing. However, in cryogenic conditions, most of the environments are having a magnetic field, and therefore, PT100 is well suited above 40 Kelvin. It is acceptable in a magnetic field environment. It is important to note that proper care has to be taken while mounting an RTD. I just told you that RTD mounting is very important, and here you can see that I have got a sensor sitting over here, and I got leads of this sensor which is running to, and over that I have put some Teflon wire so as to ensure that the Teflon, the PT100 is kept in proper thermal contact over here. Normally this is also not allowed, but I had to see that this holds, this gets stuck to that space over here. Otherwise, I should not even in fact put pressure on this sensor, because putting the pressure on the sensor also can change the sensor characteristics. So, you can just example how the RTD has been put in place over here. The unwanted mechanical and thermal strains cause a change in the electrical resistance. So, this is actually an example of what we should undo also, although we have done over here. So, we should not have tight, we should not press this sensor against, we should not put force on this, because of which the calibration can sometimes get changed. These changes induce error in the measurement. So, I should ensure that there is no mechanical strains or thermal strain that is caused on the placement of an RTD over the surface temperature to be measured. The effect of lead wire resistance is very crucial. The very important thing is the lead wires are of very long length, and therefore, it will have its own resistance again, and therefore, the effect of lead wire resistance is very crucial in the accuracy of a RTD. In order to minimize this error, two different wiring arrangements are used. This is very important that if you want to do very accurate measurements, I have to worry about the lead resistance, because these wire lengths are very high, and higher the lengths, higher is going to be the resistance of this wire, and this resistance will figure in your measured voltage or resistance across the RTD, and therefore, one has to minimize this error, and therefore, what we see is very important. So, there are different arrangements, and these arrangements therefore are called, one is called as 2-wire arrangement and other one is called as 4-wire measurement. Let us see now a 2-wire measurement. The schematic of a 2-wire measurement is as shown over here. So, this is my PT100 and this is the lead, and this is corresponding resistance of that lead wires. So, the longer the length, it will have a longer resistance, and the voltage I am going to measure actually is going to be basically because of the resistance change that will occur at low temperature, which is what this sensor sees. But in addition to that, I will have this resistance R on this side and this resistance R on the other sides also will figure up in this voltage measurement, because the lead wires which bring this voltage to room temperature also will have its own resistance, and that will also come into this voltage measurement, and therefore, this voltage measurement will have error. It will not talk about the voltage change that is going to occur at room temperature only. Let the resistance of each of the lead wire be R ohms. The ohm meter V across the ends of the lead wire measures the combined resistance of RTD plus leads. So, my voltmeter is going to measure the voltage change that is because of the temperature change over here plus the resistance that occurs over here. Okay. It is clear that this extra lead wire resistance is the direct error in measurement. So, I will have to worry about this also, that can I take this R into account, alright. Hence, the lead wire resistance should be as low as possible. So, if my measurement has to be very accurate, I will have to worry about this lead wire resistance also, and while calibrating then I will have to take this into account, alright. So, this is going to be a very crucial arrangement if my measurement has to be very, very accurate. In such arrangements, the wire of short lengths are used to minimize the resistance. So, normally what you should do? You should have a minimum length wire, so that the resistance in that case also is going to be minimum. But how to overcome this? I can overcome this by having a schematic of a 4-wire arrangement as shown. So, I can have a 4-wire arrangement instead of a 2-wire arrangement over here. So, as shown over here, I got 4 leads now, 1, 2, 3 and 4. One is passing the current and other one in parallel to this to measure the voltage across the sensor only, alright. An external constant current source I, typically in milliamps, is used to power the RTD. In this case, I have got the same source. This only sends the current and this only sends the voltage, and therefore, this voltage measurement will have some resistance figuring in there. However, in this case, I have got a different source to send the current in and different measurement to measure the voltage or resistance across the sensor. So, these two arrangements are different. This is therefore called as 2-wire, in which the source, the current and the voltage measurement or the resistance measurement is done by the same at the same place, while in this case there are different things. So, external constant current source, typically in milliamps, is used to power the RTD. The measurement leads are connected in parallel across the RTD. So, here I am measuring the voltage across parallel to this. In this arrangement, the current flowing across the measuring leads is negligibly small. When I am doing the voltage measurement here, the current flowing through this arrangement is going to be negligibly small, because I am doing here voltmeter measurements, alright. So, here is going to be different than the 2-wire arrangement that we just showed. The current being negligibly small, the voltage drop offered is also very, very small. So, I is actually very, very close to equal to 0, and therefore, there is no resistance drop or voltage drop across these leads, alright. This is completely taken care of, while this cannot be taken care of over here, because I got a current source also in the same circuit. The output of the sensor, either voltage drop or resistance, is directly proportional to RTD resistance. So, in this case, whatever voltage I see or whatever resistance I see is going to be the resistance across the sensor itself, and it has got nothing to do with the resistance across these leads, because the current flowing through these leads is going to be almost equal to 0, is negligible. So, always if I want to do very accurate measurement, I will always prefer to have a 4-wire measurement than having a 2-wire measurement, alright, and this is the way a 2-wire and a 4-wire measurements work. Therefore, the reading of a sensor is insensitive in this case to lead resistance. In a 4-wire measurement, the reading of the sensor is going to be insensitive. Now, I can use a very long length also basically in this case, provided the long length is attached directly across the sensor and it is then attached to the voltage or a voltmeter or a ohm meter. So, some of the commonly used metallic RTDs are PT100, normally platinum 100, PT1000 also could be used. There is a PT500 also nowadays which are available in the market. What does it mean? PT100 implies the sensor has 100 ohm resistance at 0 degree centigrade, alright. So, that is why the PT100 name comes. So, PT1000 will the same definition will have 1000 ohm resistance at 0 degree centigrade. So, you can have a more sensitivity, you can have a good scale in between if I use PT 1000 compared to PT 100, but if they are calibrated, it does not make any difference. All right. So, the summary of the temperature measurements related to thermocouple and RTDs is, in cryogenics, there is a need to monitor various properties like pressure, temperature, liquid level, etc. for safe operation. Thermocouple works on Seebeck effect, which is what we saw. The voltage change occur because of the materials A and B and the temperature difference T1 and T2 between the two junctions. Different types of thermocouples, what we saw are T type, which has got a copper and copper nickel alloy as a two metals working between 3 to 673 Kelvin. Then we got a K type, which is chromel aluminum, the copper constant and chromel aluminum, nickel chromium, nickel aluminum between 3 to 1543. And then we got a E type, which is nickel chromium and cupronickel. So, you got a chromel constantan alloys here, which is working between 3 to 953. You got a T type, K type and E type thermocouples normally being used in cryogenics. Then we got a platinum 100s or PT 100s and PT 1000s as RTDs are some of the commonly used RTDs in cryogenics. And in order to minimize errors due to lead resistance, which is what we just saw, 4-wire arrangement is preferred over 2-wire arrangement. All right, which is we just saw the schematic of a 4-wire arrangement over a 2-wire measurement. Thank you very much.